let's go. And okay, what I got for today, a small demonstration on load regimes. Usual something system and load nodes. So small demo I have prepared. What can we see at a connection point? I have a demo schematic. Voltmeter. I have active power wattmeter. I have instrument to measure cosine phi. I also have active meter. This one is powered from the AC source, and maybe I do it in yellow. I have a scope connection to C from E, and what I have an device which allows me to shift a current angle. Yes. From this device, I have a current. What? Current return. And this one also has. Here I have and it's powered from the second voltage. What are these voltages? This device also use the second voltage. Oh, and I forgot one more element. I have 0.1 ohm resistance, and a signal for the scope current as a time function. One more. I forgot I have also ampere meter here. Here is my schematic. What instruments? What about this one? It's labeled rotating field model. Oh, idea. First coil system powered by one and one, let's say, is oriented like this. Second coil system is supplied by second voltage, and it has an angular shift of 90 degrees. And more space like this. And I have a secondary coil. What it can be rotated. Let's say it's produce voltage out of voltage. As I draw, it is coupled with the magnetic flux. Maybe let's say it's the way magnetic flux P1. Sorry. So it's coupled with the coil system or winding system powered by O1. So in this case, I can predict what reading will be in the first voltage direction. I can rotate my coil in this direction. So it will be coupled with the flux 2, and this will be the second case. So with rotation of this coil, changing its angle relative to the system base, I can receive, or I can have any angular shift between network of first and second voltage and the output voltage of this coil. It's loaded with the current circuit and small resistance, so I get current, and this current can be shifted to any angular position. I can simulate any load regime. Let me switch to my demo table. Let's turn the light on. So what we got here, this is volt method, angle method, active power, reactive power, and current in amps. Also, yellow line will be voltage, blue line will be current, and the red line, let me switch on. The red line here is an instant power. The third line is an instant power. It's a result, it's a product of the instant voltage values and instant current values. Yeah. What a regime we have now. I will make it more visible. Now current is on the one axis with the voltage. This is what kind of regime do I have? 100 volts, I have artificial 100 volts network, 1 power factor, pure active load. Uh, 13 units of active power, it should be multiplied by 5. So it's 70 watts. And 0 units also should be multiplied by 5. 0 units of reactive power. Current 7 amps. Now, next regime with a cosine phi 0.7. You can see now current, let's say delayed or lagging relative to voltage. We have a regime, take a look here, 10 units of active power and 10 units of reactive power. I can draw a power triangle. This will be active. This will be reactive power. 10 units and 10 units. Something like this. This is active power plus reactive power is N phase shift angle plus P plus Q. It's equivalent to active load plus inductance. I can also draw currents to make it more visible. Here is voltage vector. It's U1 picture. And current lagging 45 degrees. The blue current. Okay, I draw white. This will be white. Here is the current vector. Resistance plus inductance. Resistance plus coil. Now I have 45 degrees shift. It's not very usual. Normal cosine will be something like this, 0.85. This is usual mode for networks. Let's take a look on a red line. Cosine P or power factor 1, angular shift 0. You can see instant power. This red line is an instant power. And we should, to get a power, we should integrate one division is 10 milliseconds. So from this point to this, we need to integrate and we will get active power. You can see it's a positive. Now, visible, make it more visible. 0.7, phase shift 45 degrees, and you can see this negative parts or negative intervals in instant power. This means what we have an reactive power, and we're consuming 10 units, it's a 50 watts of active power, and 10 units, red scale should be used, and 10 units of reactive, 50 volt amps reactive. We're consuming them from the network. Mirror regime. What do we see? It's a kind of mirror regime. Power factor, same, 0.7, but now leading current. 10 units or 50 watts are consuming from network, and minus 10 units of reactive power, you see. It's a capacitance mode. Now we consume active power from the network and we send reactive power to the network. You see, current is leading, corresponding to the voltage. I'll draw it in green. Here is active load plus capacitance. Current, active plus capacitance. I can go further. Zero active power. You can see current still flows, voltage unchanged, but no active power consumed. We only supply reactive power to the network. pure, now we see regime of pure capacitance. In opposite, here it is 0. 0 active power, 15 units of reactive power consumed. Current is lagging relative to the voltage. Ideal coil, ideal inductance. We only take reactive power from the system. So take a look on the red line. It's kind of oscillation. Energy taken from the net to energize magnetic system of the ideal coil and then sent back to the network. Real active energy consumption now is 0. Okay, now it's a half of the mode. Now let's go forward. 0 active. Let's take more. I have more. Let's say lagging. I'm going forward. And where am I? Minus V. Take a look what's going on. 10 units of active power, but with the minus sign. This means what 50 watts now are sent to the network. In the same moment, 10 units of reactive power are consumed from the network. I have negative active power and positive reactive power. Something like this. It's a generator regime now. Now connection node sends active energy to the system. It's like minus F and minus capacitance, non-capacitance, inverse regime. Here is the current. Here is current. 45 degrees. So current now, we may say it's lagging by 90 plus 45, 145 degrees. Here is the current for minus R plus regime. You can say minus R. It's a generator regime. For synchronous machine, it's an under excitement regime. For synchronous generators, generator it will be regime when it carries or it sends carries active loads or sends energy to the network, but excitement current is below necessary and machine consumes reactive power from the grid. Next, I would like to go this way. Yeah. Characteristic regime, minus 15 units of active power and 0 reactive. it is here, generator, 180 degrees angular shift, and you can see zero reactive power, but active power is with a minus sign, is negative. Meaning what we not consume power, we send active power to the grid, and we have a zero reactive power balance. This regime, 0,9, we send active and we send reactive power. To make it more visible, I'll switch. This is a bit artificial, but it's 0,7 power factor, angle of 45 degrees. Now, our node is sending 50 watts of active energy to the grid, and it also supplies 50 watts to the grid over a regime of overexcitement. Machine generate this minus case current for such regime. It's like R plus A minus. It's also generator regime. See, for synchronous generator, it will be, look at the angular shift and instant power. It will be regime or mode when machine carries an active load, but it also supplies reactive power to the grid. Machine is overexcited. Exciting current is above 1 pu, above 100%, to supply network with the reactive power. More typical will be something like this, with a little overexcitement, or maybe this one, small underexcitement. Regime of synchronous condenser. Synchronous machine supplies very little active power, maybe zero, and supplies network with the reactive power. Another this. This is also synchronous condenser regime. Very small active power, maybe even for pure synchronous condenser it will be consumption of active power, and machine absorbs reactive power from the network. It may be necessary, for example in vertex region at night time, when we capacity of high voltage line produce, say overproduce reactive power, so its power needs to be absorbed. So such a regime of synchronous condenser may be used to absorb excessive reactive power, thus making network stable, preventing overvoltage. At the daytime, synchronous condenser regime like this may be required. Very small active power taken, and active power supplied to the network to compensate reactive power supplied to the network to compensate reactive power needed by asynchronous machine. Ideal active load, no reactive power consumed. Here, so-called four-quadrant system, load regimes, generator regimes. Active for inductive, so inductive load, capacitive load. Minus capacitive means what we supply grid both with active and reactive power. Minus here, minus. And this red regime minus active minus inductive means what we supply network with both active and reactive power. Here we supply active and consume or absorb reactive. Here it is.